In this video, we're going to look at how we can take our data from our torsion test in order to determine the modulus of rigidity of our material. So where this might be useful is if you had some test data and you wanted to determine what the likely material was that was used in the test. If we can determine the modulus of rigidity, which is a property of a given material, we can then go some way to determining what the material was that was involved in the test. In the example we're going to look at here, I'm going to use the test data that was obtained in a torsion test for 0.4% carbon steel. And if you haven't already done so, you can go back and watch that video in order to see how the test's conducted and how the results are collected. So to begin with, what we have is the angle of twist that the specimen is being subjected to. Now, in the practical demonstration, we discussed how the machine would produce an audible click for every partial revolution of the shaft. And we also talked about how each of those clicks or how each of those partial revolutions was equal to an angle of twist of 0.3 degrees. Now, as we know from an earlier tutorial, in the general torsion equation, the angle of twist must be inputted in radians. So the first thing that we need to do is take each of our angle of twist in degrees and convert them into radians. Now, the simplest way to think about this conversion is we need to multiply by the number of radians in a circle and then divide by the number of degrees in a circle. So to input a formula, we need to start with equals. We need to click on the cell that we're converting from degrees to radians. We need to multiply by the number of radians in a circle. So Shift 8 for multiply. The number of radians in a circle is 2 pi. So we need to do 2 times pi, and there's actually a function for pi, pi, but we need to remember to do open and close brackets in order to input that value of pi. So far we have the value in degrees times 2 pi, which is the number of radians in a circle, but then we need to divide by the number of degrees in a circle. Well, the number of degrees in a circle is 360, so divide by 360. So times 2 pi over 360. We can then copy that formula down. And that will populate that column for us. Now, if you're not comfortable with the conversion there, then you could have done the conversion of times 2 pi over 360 in your calculators and then multiply each of the values in this column by that conversion factor. 2 pi over 360 is actually 0.01745, so you have the option to do it that way if you prefer. But since we're using Excel, we may as well use the functions that are available in Excel. Okay, so now we have our torque values that were required in order to achieve those angles of twist. And the final column is the stress that's acting on the sample. Now, we know from an earlier video that the stress from the general torsion equation is T times R over J. So on the right-hand side here, I have some data for our test piece. The test piece had a diameter of 6 millimeters and a length of 80 millimeters. But what we're going to need is the radius in meters and the J value in meters to the fourth. We need those both in SI units. So in order to determine our radius in meters, we need to halve the diameter, giving us 3 mil, and then divide by 1,000, giving us 0.003 meters. And for our J value, we're going to use a formula. And the formula for the J value for a solid shaft is pi d to the fourth over 32. Again, we saw that in the earlier video on applying the general torsion equation. So equals pi, well, we've already said we can input pi by doing pi, open brackets, close brackets, times the diameter to the fourth. Well, we have the diameter in millimeters, 6 millimeters, but we need to input that diameter in meters, or 0.006, and we need to raise that to the power 4. Well, to the power of in Excel is Shift 6. And finally, we need to divide all of that by 32. Now, the way I'm going to do that is by putting a bracket in front of pi I'm going to put a bracket after to the power fourth and then do divide by 32. So pi d to the fourth over 32 gives us a j value of 1.272 times 10 to the minus 10 meters to the fourth. So now we have everything we need to calculate our stress, because stress is T times R over J equals, we need to click on the torque value because as the torque value changes, the stress changes. We know the radius is 0.003. Alternatively, we could have cell referenced H3 there. And our J value, here I'm going to use the cell reference, divided by H4. Now, when we paste that formula down, we don't want H4 to change to H5, H6, H7 and so on. So what we need to do is absolute cell reference this H4. And the way that we do that is by putting a $sign in front of the H and a $sign in front of the 4. I'll show you what this does in a moment. So let's copy this down a few cells. And we can see the value of stress is increasing. If we click on a later cell, here, you'll notice that the value of D3 has changed to D6, but the absolute cell referenced value of H4 has remained as H4. Now we do have one more modification to do here because I've calculated the stress in pascals, and we actually want that in megapascals. So to get from pascals to megapascals, we need to divide by 1,000,000. So here, in my formula, I'm going to put a bracket at the start, a bracket at the end, and I'm going to divide by 1,000,000. So divide by 1 with 6 zeros. 1, 2, 3, 4, 5, 6. And now I'm happy with that. I can paste that formula down to the bottom of the column. Like so. Now when the test was carried out, some data was missed. So what I'm going to do is just remove these sections here for the missed data, as otherwise that will impact on our graphs. And I'm going to plot two graphs. Now the first graph that I'm going to plot is angle of twist against torque. Now recall that the general torsion equation came in three parts. T over J equals tor over R equals G theta over L. So T over J equals G theta over L. I'll just make a note of that over here. So let's plot the graph and see what we're left with. So I'm going to highlight the two columns. I'm going to do insert, scatter, and I end up with a graph that looks something like this. Now this graph represents all of our data, but in actual fact, we can only determine the modulus of rigidity during the elastic deformation stage. So the first thing that I'm going to do is I'm going to amend my angle of twist axis at the bottom. So if we click on Design in the menu at the top, and if we go to Quick Layout, then we can choose a layout that includes our legends. Our x-axis is angle of twist in radians. And our y-axis is torque in Newton meters. Now, just so we have a little more space here, I'm going to remove the title. So we can see clearly here that the elastic deformation is complete after considerably less than 1 radian in terms of angle of twist. So let's modify this axis. We have right click, format axis, and let's set the maximum value on that axis to 1. Okay, so as we inspect this further, we can actually see that all of the elastic deformation is complete within the first 0.2 radians of twist. So let's modify that further. and we'll set that at 0.2. Okay, so our graph looks a lot different now. And what we have on our graph is we have a linear section, and at the end of that linear section, our plastic deformation will begin. Now what we need to try to do from this graph is determine where that linear section ends so that we can determine the gradient of our graph for this particular material. Now, because I want to be able to put a trend line on this graph, I need to remove all of the data that doesn't represent elastic deformation. So to ensure that I remove sufficient amounts of data, I'm going to remove all data after an angle of twist of 0.08 radians, because I don't want that data to skew my results. So let's move the graph for a moment. And I'm going to remove all of the data up to an angle of twist of 0.08. And by remove the data, I mean I'm going to delete it for the purpose of producing the graph. So I'm going to remove all of that data, and then I'm going to return back to my graph. I'm also going to adjust this axis once again. Let's set this as 0.1. Now what I'm really trying to do here is hone in on the data that's relevant to me. I want to hone in on the data that represents elastic deformation. And now I've isolated that data, I can add a trend line. So I go right click, add trend line, and I'm going to add a linear trend line because we know that during elastic deformation, that relationship should be linear. Let's add some minor grid lines. So add minor grid line. And let's add some minor grid lines over here. Okay. Now in order to take the gradient of this graph, normally we would need 2 points. We would need a point at the top end of the line, and we'd need a point at the bottom end of the line. But if we look carefully, we can see that this line goes through the origin. Therefore, if we take a point on the line where we can determine the x-coordinate and the y-coordinate, we'll be able to easily determine the gradient of this line. And I'm going to take this point here. At this point here, we can see that the torque is 3 Newton meters. And we have an angle of twist there of 0.064. We can see from our scale that each of these increments equals 0.004 because we would have 0.064, 0.068, 0.072, 0.076 before we get to 0.08, so 0.064. The gradient of this line then is just going to be 3 divided by 0.064. We can do the sum over here, equals 3 divided by 0.064. The gradient of that graph then is 46.875. Let's make a note of that value and see how we can use that to determine the modulus of rigidity of our material. Just note that the graph we have here is torque against angle of twist. Therefore our gradient, change in y over change in x, is the same as t over theta. So we have t over theta equals 46.875. Okay, so let's go to the top. Now if t over theta equals 46.875, then we need to look at how we can modify this formula in order to use that. Recall that we're trying to calculate g. Well, in order to get g on its own, we need to multiply each side by L and then divide each side by theta. So we'll get g equals TL divided by j theta. But the gradient of our graph represents t over theta. So let's separate this out, and instead we're going to write g equals t over theta times L over J. Now, it should become a bit more apparent why we've separated the formula out in this way, because we know from the gradient of the graph that T over theta equals 46.875. We have a value for L of 80 millimeters, and we have a value for J. Therefore, G for this material equals T over theta, 46.875 from our graph, times the length. Well, 80 millimeters, remember to convert to meters, is 0.08 meters. And J we have in cell H4, so divide by J, close brackets, equals, well, the value that we see there is the modulus of rigidity in pascals, but it would be more sensible to express that in gigapascals. So all we need to do is divide that answer by 1 billion, or 1 with 9 zeros, and we get a modulus of rigidity equal to 29.47. So it's quite a complicated process, but we're going to repeat it, except this time we're going to use the angle of twist in radians and the stress in megapascals, just to see how that process differs. So we're going to create a new graph, angle of twist in radians against stress in megapascals, and we're only using the data for the elastic region, so already that makes things a little bit more straightforward. We do insert, and we get our scatter graph. We can add some legends on there by doing design, quick layout. Once again, we're going to remove our title and our series legends just to create a little bit more space. The axis on the bottom is our angle of twist in rads. And our y-axis this time is our stress in megapascals. The next thing we did was to add a trend line. And we also want to add some minor increments or minor grid lines to our graph. And then we can pick any point along that graph in order to get our gradient. So this time, our gradient is going to be stress over angle of twist, because we have change in y over change in x. And again, it runs through the origin here. So in order to determine the gradient of that graph, we just need to pick any point on the line and do the y variable over the x variable. So this time, let's pick this point here, which clearly sits on the line. And we have a stress of 50 megapascals. And we have an angle of twist of 0.046. This time, each of these represents 0.002, as we can see from our scale. So we have equals 50 megapascals, well that's 50 million, or 50 e to the 6 in Excel. And at 50 megapascals, we have an angle of twist of 0.046. Okay, so we have a much bigger number this time, and this number represents stress over angle of twist. Stress is tau. So stress over angle of twist, like so. So this time we need to return to our general torsion equation, but this time we have stress and angle of twist. So the two terms from the formula that we would need to use would be tor over r equals g theta over L. So we have tor over r equals g theta over L. But we need to rearrange that to make g the subject. So we need to times each side by L and divide each side by theta again. So we get tor L divided by r theta. And that's g equals . Now we're going to separate this out like we did in the previous example. So in actual fact, what we have is g equals tor over theta. We need to get tor over theta together because we have a value for that based off the gradient of our graph. So tor over theta times L over R. Like so. So we have a value for tor over theta based off the gradient of our graph, and we have values for L and R in meters. So we can do equals tor over theta times, well, our length was 80 millimeters or 0.08 meters. And our radius is 3 millimeters or 0.003 meters. And once again, we get a value in pascals from that formula. Now we can repeat what we did before in order to get that into gigapascals. And all we did was divide our pascals answer by a billion. So equals, a billion is the same as 1 times 10 to the 9, or 1 with 9 zeros. And once again, we get an answer in the order of 29 gigapascals. So we've seen two different methods there. We plotted a graph of torque against angle of twist, found the gradient, and determined the g value using t over theta times L over j, which was just a manipulation of the general torsion equation. And we found that the modulus of rigidity of that material was 29.5 gigapascals. We used a second method where we plotted the shear stress against the angle of twist, and then we found the gradient of the graph, which represented tor over theta, or the stress over the angle of twist. We were then able to use that value in the formula below, g equals tor over theta times L over r, in order to determine the modulus of rigidity as 28.99 gigapascals. So as we would expect, the two methods give a result that's very, very close because they were derived from the same set of data. So the modulus of rigidity of the material under test we can assume is 29 gigapascals.